Well, our lecture for today is settling and sedimentation in particle fluid separation. Application of settling and sedimentation include removal of solids from sewage waste, settling of crystal from mother liquid, separation of liquid-liquid mixture, settling of food particle from liquid food, and settling of slurry from soybean leaching process. Particles could be solid particle or liquid drops, while fluid is liquid or gas, and it may be at rest or in motion. What we mean exactly in that, if we imagine we have liquid here containing particles of solid, and that at rest, at time 0 the level will be here, t equals 0. As time movement, so the liquid level of particles will be changed, and this process continues till we get a layer of solid in the base of container or vessel, and here we have clear liquid. So conventional surface water treatment, we have raw water passed through screening, and screening will prevent sludge. Then we add alum polymers and with rapid mix, and we have unflocculation. Flocculation, also named aggregation, or augmentation, which means collect of particles together and formation of large particle which will be settled faster. Then sedimentation, and also will produce the sludge. Then pass to filtration, then disinfection with chlorine, then storage, then to distribution to the houses. Bioprocess overview, upstream processing, intracellular product or extracellular product. What we mean here, that we have a cell, and we have inside the cell an process occurs, and this process will be either chemical or physical. That process will be called intracellular product. Whether extracellular product, all cells have extracellular polymer substance, and maybe will be trapped several particles here in this spaces and settle down, and that is a kind of system defense of microorganisms. Then here, cell disruption, when particles move to the cell, cell will disrupt, and by chemical or enzymatic or mechanical or physical process. Then solid liquid separation by centrifugation, sedimentation, extraction or filtration. Then will be concentration by evaporation or ultrafiltration or adsorption or precipitation. Then purification stage by chromatography. Then formulation, crystallization, freeze drying, spray drying, and sterile filtration, and final product. Settling of particles from suspensions depends on characteristic of the particles and concentration of particles in suspension. So we have discrete particles, particles whose size, shape, and specific gravity do not change with time. Fluctuating particles, particles whose surface properties are such that they aggregate upon contact, thus changing in size, shape, and perhaps specific gravity with each contact. And we previously explained that particles like this start to aggregate through extrapolar polymeric substance and will be settled or move faster than other particles. Dilute suspension, suspension in which the concentration of particle is not sufficient to cause significant displacement of water as they settle, or in which the particles will not be close enough for velocity field interference to occur. What we mean here, that particle is not sufficient to cause significant displacement of water. Each particle, when it settles down, it will remove quantity of water, and as this particle is very small, there is no displacement of water. Finally, concentrated suspensions, suspensions in which the concentration of particle is too great to meet the condition mentioned for dilute suspension. Here we have very high concentration, so the sedimentation process will be very difficult to achieve. This table shows that discrete particle settling, type 2 flocculate settling, and type 300 settling or zone settling, and type 4 compression settling. Each type here in this table will give properties and example of that, and I leave that for you to read. Now we try to define free settling. Free settling, if the particle is at a sufficient distance from the wall and from other particles so that its fall is not affected by them, ratio of particle diameter to container is less than 1/200. Or if the particle concentration is less than 0.2 volume percent in solution. What we mean here, at the wall will have an effect on the particles. So we assume that we have large diameter, so we can neglect the effect of the wall, and velocity is not very high, so each particles will settle alone without effect with other particles and effect of the wall. The 100 settling, particles are crowded. They settle at lower rate. The separation of dilute slurry or suspension by gravity settling into clear fluid and the slurry of higher solid content is called sedimentation. Theory of particle movement through a fluid. Number of forces will be act on a particle moving in a fluid. Density differences is needed between particles and the fluid, and that will be buoyancy force, depends on F B. External force of gravity is needed to import motion to the particle, gravitational force, and that will be Fg. Resistance, or for a rigid particles moving in a fluid, there are three forces acting on the body: gravity acting downward, buoyancy force acting upward, and resistance or drag force acting in opposite direction. Assumption and derivation. Sphericals, we will assume that we have spherical particles, non-porous, i.e. porosity equals 0, incompressible fluid, large diameter to neglect wall effect, as we say later. Spherical, non-porous, incompressible fluid, large diameter to neglect the effect. So we will see that gravity force take the particles down, and the drag and buoyancy force take the particle upward. So if Fg larger than Fb and Fd, then particle will be settled. If not, particle will still hold constant. Buoyant force Fb in a Newton on particle is Fb equal m phi rho phi g over rho the particle, that will be v the particle phi rho phi g. M, mass of particle kilograms. Following particles, which we mean that particle will be full in the fluid. Solid density, rho liquid density, and g where gravitational acceleration meter per square second. Gravity force in Newton on particle is Fg تساوي m في g. Sometimes we can put m في a. Drag force Fd in Newton on particle is proportional to the velocity head u تربيع over 2, and this is no more kinetic energy of fluid displacement by moving body. This must be multiplied by density of fluid and by area. So Fd equals Cd u تربيع over 2 rho phi multiplied by area. And Cd is the drag coefficient dimensionless. A projected area of particle. What do you mean projected area? The area in the direction of flow. So Fg minus Fd equal force due to acceleration equal m du over dt. And here m is the mass, du over dt is acceleration, which is variance of velocity with time. So m du over dt will be equal to mg minus m في rho في g over rho d, rho particles, minus cd rho au square over 2. Fluent particle consists of two periods. First one, accelerated fall, very short, about 1 over 10 seconds. Then the second, constant velocity fall. The velocity is known as resettling or terminal velocity. Take du over dt equals 0 in equation 4. Here, if we put du over dt equals 0, this because we assume that terminal velocity will be constant. So we will get u t, to terminal velocity, 2g rho p minus rho phi m over a rho p cd phi rho. For spherical particles, we have m equal to pi dp تكعيب rho p over 6 and a تساوي pi d تربيع over 4. So terminal velocity will be square root 4 rho p minus rho d particle g over 3 cd phi rho. Ut is in meter second, g equal to 9.81 meter per square second, dp in meter. This figure shows the relation between Reynolds number for spherical particles and the friction here, r dash over rho u تربيع. And this figure is similar to the figure 3.7, which we take in fluid flow. So region A and region B and region C and region D. And this, we're talking here about spherical particle as we assumed. So drag coefficient on sphere, since we say that Vt, some reference named it Vt or Ut. You could write Ut or Vt. First area, which we called Stokes law. Fluid here is laminar and Reynolds is small with this, and Reynolds number in this place is turbulent, here turbulent boundary layer. So if we take log Reynolds, the particles, and log CD, we will see also 4 places. First one is the Stokes law, intermediate, Newton's law, and boundary layer separations. Relations between R over rho تربيع and Reynolds number. The relations between R dash over rho تربيع and Reynolds can be put in graphical form in which 4 regions can be distinguished. Regions A, Reynolds أكبر larger than 10 to minus 4, less than 0.2 to 1. In this region, the relations between r dash over rho u and Reynolds number is a straight line of slope minus 1. And the drag coefficient is CD equal 24 over RE, or R dash over rho u square equal 12 over Reynolds, and Reynolds UT rho d over dt. This relation, you don't have to keep them, but you have to know when I said Stokes law, you will use this equation or this equation. So equation 6 becomes ut equal to d particles square rho p minus rho over 18 mu, and this is a Stokes law. Regions B, Reynolds larger than 0.2 to 1, less than 500 to 1000. In this region, the relationship between r dash over rho square and Reynolds is r dash over rho square equal 12 or 12 over re dash 1 plus 0.15 Reynolds power 0.687, or this relation. Also, this relation will be given in exam. So you need to check Reynolds, then decide which area or which part you have to work, A or B or C or D. Region C, Reynolds larger than 1000, less than 2 to 10 to 5. In this region, the value of r dash over rho square is constant, which will be 0.22 on CD equal to 0.44. And region D, Reynolds less than 2 power p multiplied 10 power 5. In this region, the flow change to turbulent and separation of boundary layer occurs at the rear of the object. The value of r dash over rho square is constant, will be 0.05, and CD will 0.1. So drag coefficient and drag forces on particles given in these tables according to the regions A, B, C, and D. We are give drag coefficient and drag force. You have to learn how do we reach this force and this force and this force and this force, and that will be homework. You have to solve it and send it to me. The above equations were based on the assumption that the settling of the particle is not affected by other particles free falling and that there is no Wall effect. Here we have example: particles 2 millimeter diameter and density of 205 kilogram per meter cube is settling in a stagnant fluid in the Stokes flow regions. So here he said to me that this is Stokes flow regions in regions A, and I must go to the information of region A, and I have to know which equations belong to these regions. So he wants to calculate the viscosity of a fluid if the fluid density is 1000 kilogram per meter cube and particle falls at a terminal velocity of 4 millimeter second. So here he gives me terminal velocity, which is 4 millimeter per second. What is the drag force on the particle at these conditions? What is the particle drag coefficient at this condition? What is the particle acceleration at this condition? What is the apparent weight of the particles? So in Stokes region, we have this equation: ut equal x terbi rho p minus rho with g over 18 mu. Ut given, rho f given, rho p given, distance given. So we can compute the viscosity, which will be 0.8175 pascal second. Then we can compute the drag force from this equation: Fd equal 3 pi mu ux. So we can compute the drag force. Drag coefficient also from the relation CD equal 24 over Reynolds. CD 24 mu over rho ux. So we have the drag coefficient. At terminal velocity, acceleration is 0, and why? It is obvious. We constant velocity since m or equal to du over dt, since this is 0, so this is 0. Apparent weight at terminal velocity, apparent weight, the drag force equal to 6.164 multiplied 10 to minus 5 Newton. As a check, we calculate the apparent weight, pi x cube over 6 rho p minus rho f fit g. So we have or get the same answer. Example 2, a cylindrical bridge pair 1 meter in diameter is submerged to a depth of 10 meter in the river at 20 degrees centigrade. Water is flowing past at a velocity of 1.2 meter per second. Calculate the force in Newton on the pier. So we have here cylindrical bridge, 1 meter diameter, and submerged 10 meter in the river at 20 degrees centigrade. The flow of water is 1.2 meter second. You want to calculate the force in Newton on the pier. We have rho water at 20 degrees centigrade, mu water also. So Fk equal to CdAp rho u square over 2, and Reynolds, we have to compute Reynolds. From the figure, Cd equal 0.35, projected area will be d phi L, which means that the submerged part multiplied by width, the 10 phi multiplied by 1. So Fk equal 0.35 over 2 phi 10 phi 998, which is 0, and this is the velocity, so 2515 Newton. 100 settling. Settling velocity is less than free settling for Stokes law. The drag force is greater in the suspensions because of the interface of other particles. What we mean here, when I have one particle here, which will fall due to Fg, and here F buoyancy and F drag force. As in free settling, we assume that there is no contact between particles, but here we have effect of other particles on each another. So drag force will vary in this case, and drag force will be greater in the suspension because of the interface of other particles. This higher effective viscosity of mixture. So also viscosity will be varied here, is equal to the actual viscosity of the liquid itself divided by an empirical correction factor psi p, which depends upon porosity or volume fraction of a slurry mixture occupied by liquid. So mu mixture will be equal to mu over psi p, and the psi given by this correlations 1 over 10 power 1.93 multiplied by 1 minus porosity. It is dimensionless, and density becomes rho m psi rho fill E minus 1 minus porosity phi rho p. So when we say rho phi m, we mean that this part occupied by water, this part occupied by slurry or particle. Rho mixture is density of slurry in kilogram solid plus liquid per meter cube. Then we will get rho p minus rho m equal rho p minus rho m, as in equation 12 here. We substitute by rho m by this, so we get porosity phi rho p minus rho. Settling velocity with respect to apparatus is porosity times the velocity calculated by Stokes law for laminar. So we have here, this is porosity or settling velocity, and this will be multiplied by porosity, and we get ut in 100 settling. So instead of porosity, we'll put porosity square psi p. And Reynolds will be no more than dput rho m على mu m في porosity. So we will get Reynolds in this form. This figure gives the relation between volume fraction of liquid in slurry porosity and psi p, or porosity تربيع في psi p, and we can use it to compute if I have volume fraction of liquid in slurry and this curve for psi تربيع في psi p and this curve for psi p equal mu over mu mixture, and we can compute psi p or eta of psi تربيع في psi p. Example 3, oil droplets having diameter of 0.02 millimeter are to be settled from air. Here we have oil droplet. We will consider it as a particle having diameter 0.02 millimeter are to be settled from air. So my fluid here is air at an air temperature of 37.8 degrees centigrade at 100.01.3 kilopascal, and density of oil is 900 kilogram per meter cube. Assume the drop is rigid sphere. So here he told me to assume it is rigid sphere, but if he don't, I have to assume that this oil drop is rigid sphere. Calculate terminal velocity of the drop given that viscosity of the air is 1.98 multiplied by 10 to minus 5 Pascal second. So firstly we have to compute raw oil air, which will be P for molecular weight over RT, and this is from universal gas relations, which is PV equal an RT. So after I compute rho, I have to find the Reynolds number for a fluid in terms of UT. So UT here will be 4 rho P minus rho في dP في G over 3C dP rho. So I'll solve this for CD, will be 0.0267 over UT squared. So I have equation 1, equation 2. This will be solved by iteration. Assume UT, find CD, then plot on the figure, then from computed line intercept with original line we find get UT and Reynolds, which will be less than 1, or here assume UT, from equation 1 we compute Reynolds, from equation 2 I compute CD until I have straight line which will give me UT and Reynolds. Example 4, glass sphere having diameter of this number settled in water, slurry contain 16% solids. So since he told me 60% solid, I have to compute porosity here, and this will be 100 settling, not free settling. Density of a glass sphere is given, density of water is given, viscosity of water also given. So we have to compute porosity, which we call 14 over 998, and this is water over rho, and this is water over rho, and this is slurry over rho. So we have porosity equal 0.622. Bulk density of slurry rho m, we compute it from this equation. Rho m تساوي porosity في rho minus 1 minus porosity في rho p. We have compute porosity, so we get rho m 1553 kilogram per meter cube. Then we compute psi from this relation. Then we compute UT from this relation also. We get 1.2525 multiplied 10 power minus 3 meter per second. And for check, I will compute Reynolds. Also, I found this is near Stokes law. Criteria are equal settling velocity for different particles. For particles of materials A of diameter dA and density rho A, Stokes law is applicable, and then the terminal velocity or terminal falling velocity U naught A is given by the same equation of free settling. For a particle of material V, UB will be the same equations. So the condition for two terminal velocity to be equal is dP over dA must equal to rho A minus rho over rho B minus rho power half. If Newton's law is applicable, so U terbi A and U terbi B is computed for equal settling velocity. In general, the relationship for equal settling velocity will be dB over dA equal rho A minus rho over rho B minus rho power S, where S here is equal to half for Stokes law region, S equal 1 for Newton's law, and as an approximation, S is larger than half, less than 1 for intermediate region, and you have to remember this correlation. Problems with unknown terminal velocity. So if we have terminal velocity is not known, Reynolds number cannot be found to decide the settling regions, and therefore the drag coefficient cannot be found. The drag force at the equilibrium condition can be written as R naught pi over 4 d terbium equal to pi over 6 d cube rho s minus rho phi g. So from this relation we get R naught equal 2 over 3 d rho s minus rho phi g, and here we will divide by rho u naught square both sides, so we get R naught dash over rho u naught square equal 2 over 3 rho u naught square d rho s minus rho phi g. In this case we use the dimensionless group of R dash over rho u naught square RE dash square, which does not involve u naught, since if we try to put this R over rho naught square and this Reynolds will be rho square d square u naught square over mu, so u naught will gone with u naught here, so we will get this terms equal 2d power 3 rho s minus rho g rho g over 3 mu, which does not contain u naught or ut. Dimensionless group d square d power 3 rho s minus rho phi rho g over mu square is called Galileo number Ga, and R dash over rho unit square Re dash equal 2 over 3 Galileo number. The group R dash over rho unit square Re dash was plotted versus Reynolds to be used in the case that terminal velocity is not known. If you don't know which regions, calculate CDRE square from the following equations. Use result to draw a line on the drag curve. For example, suppose CDRE square equal 8, then for RE equal 10 RE square equal MIA, CD equal 0.08. For Reynolds equal 1, RE square 1, CD equal 8. For Reynolds 0.1, so it's obviously that this one will be correct. In this figure, use RE with drag coefficient chart. Here, single particle Reynolds number REP with the drag coefficient CD. From this figure, we can't, at different size, we can compute the drag coefficient CD. Example 4, calculate the terminal velocity of the settle ball 2 mm diameter and of density of 787 kg per meter cube in an oil of density. So we have here steel ball and my fluid is oil with density 900 kg per meter cube. Viscosity is 15 millinewton second per square meter. For a sphere, we have used this relation, which is no more than 2 over 3 Galileo number, and we can find that is 131.3. Take log, and from table 3-4 we can find Reynolds equals 6.8, thus u naught will be 0.189, since we know that Reynolds RE equal rho ud over mu. Here rho is unknown and Reynolds is known, so we can compute u. Example 5, estimate the terminal velocity of the limestone particles d 0.15 millimeter, rho 2800 kilogram per meter cube in water at 20 degrees centigrade. So tau over rho unit square. Tau is the same of r naught or r dash. Also here 2 over 3, and this is no more than Galileo number as we shown before. So we can compute this is 39.3. From the figure, Reynolds will be 2.6. So we can compute Reynolds, then compute the velocity. Problem with unknown particle size. For unknown size of particle that have a given terminal velocity, we use this relation r dash over rho unit square. Reynolds power minus 1 will be equal to 2 mu g over 3 rho square u naught power 3 multiplied by rho s minus rho. So in this example will be leave as homework for you. And this is the end of our lecture today.